Okay, cool. For problem set 10, looking at Couette and Pascal flow finite differencing analytical numerical solutions. Finite differencing is a numerical method used to approximate derivatives by replacing them with algebraic expressions. It's built from values at nearby points, the area under the curve into rectangles, essentially. We're turning calculus into algebra. The difference between analytical solutions and numerical solutions is that analytical solutions are exact closed form expressions that satisfy a differential equation for all points in the domain. You only use it for simple geometry and simpler boundary conditions. The numerical solution doesn't have an equation, it's just a set of points, and you can use it to solve more complex problems, but there's more error involved with it than analytical solutions. Couette flow is where one plate moves while the other is stationary. There's no pressure gradient. It's driven entirely by the one plate that's moving, and it has a linear velocity profile. Pascal flow, both of the plates are stationary and is driven by a pressure gradient and has a parabolic profile, and there's no slip at the walls. Just going right into it, we're going to start with Couette flow analytical. You're assuming it's Newtonian, there's constant density and viscosity, no electric field, a steady state, no slip at the walls. There's no change in pressure, and Vy equals Vz equals zero, and it's because gravity acts vertically downward. Um, and for Couette, that basically translates into linear. The stress is constant across the gap, and the flow rate depends on the velocity and viscosity only. And we're starting with simplifying the continuity equation. We can get that down to dvx divided by dx equals zero, and then we move on to the excellence imbalance using that. And you can simplify that down to zero equals mu d squared vx divided by dy squared. And you can integrate that twice to get two different equations. And you can use those two different equations with the two boundary conditions. The first one being y equals zero, vx equals zero. And using that, you can get that C2 also equals zero. And for the second boundary condition, y equals h, and vx equals u. And you can use that to find that C1 equals U divided by H. And you can plug those numbers back into what you found up here. And that's basically a Vx as a Y equals U divided by H multiplied by Y. For the finite differencing of Couette flow, you can start again from the heuristics that I showed above, and you can use the numerical solution Vx1 of n plus 1, the one in front, minus the one behind, minus 2 Vx1, the one you're at currently, and you divide that by the change in y squared, and that equals 0. And you can simplify that down to actually solve for the velocity you're actually looking for. And you can apply your boundary conditions the same as above, and I'll show you the Excel document at the end of me actually doing that. But then we're moving on to Pascal flow analytical. And we're once again assuming this is Newtonian constant density viscosity, no electric field, steady state, fully developed flow, Vy equals Vz equals zero. And you can basically assume that dvx over dz equals zero because wide. There's no slip at the walls. And because of that, those assumptions, it's a parabolic flow. The wall stresses are in equal magnitude, but in different signs. And the flow rate depends on the pressure gradient. We can simplify the continuity equation down to dvx divided by dx equals zero. And using that, we can move on to the excellence imbalance, which we can also simplify down. This time we do the pressure gradient. So delta P divided by L equals d squared Vx divided by dy squared, because you can cross out the viscosities. You can integrate that twice to your two equations. Your first boundary condition, y equals zero, and dvx divided by dy equals zero. You can use that to find that C1 equals 0, and for your second boundary condition, y equals plus or minus v divided by 2, v of x equals 0, and you can see that C2 equals negative delta p d squared divided by 8 mu L. And you can plug that back into your velocity equation, and you can get the final velocity for it is negative delta p divided by 2 mu L is multiplied by d squared divided by 4 minus y squared. And then you can solve the Pascal finite difference equation. You're starting it from number 6 I showed above, and you're once again solving it with um, area under the curve squares and with the same boundary conditions. And I will show you the Excel at the end of the video. And once you have all of your velocities, you can move on to solving for the volumetric flow rate in the z direction for all of those. So quit analytical. It's basically the integral from your boundary conditions over the velocity in terms of y. But it's the integral of 0 from 0 to h of u h y dy. Ends up being 400 centimeters squared per second. And for the finite differencing, you're doing the sum of all of the rectangles multiplied by the change in y, which also ends up being 400 centimeters squared per second. That's in my Excel document I'll show later. But Pascal analytical, you're solving the viscosity of the boundary conditions, and the boundary conditions are negative d divided by 2 to positive d divided by 2 over the velocity that you calculated earlier. And that ends up getting you this lovely number. And Pascal finite differencing is the same concept that you had for the Couette finite differencing, just different numbers you're working with, and that ends up being the exact same thing you calculated for the analytical Pascal. And once you have those, you can calculate the shear stress at each plate and the shear force per unit width for all of them. And so basically that's just tau multiplied by shear force is tau multiplied by the cross-sectional area. You can solve for tau by multiplying mu by dvx dy over the boundary conditions you're looking at. So that ends up getting you for Couette analytical 300 pascals per times centimeters. Finite differencing, and you're once again using your little rectangles instead of actually using an equation. That ends up getting you the same equation you had before, and you end up getting 300 pascals times centimeters, same things you had for the analytical. And Pascal analytical, same concept. Your velocity is same as that, but your cross-sectional area is WL. And so you need this number of pascals times centimeters, and for the finite differencing of that same concept as the finite differencing for Couette. And you end up getting this little bit number of pascals times centimeters. And finally, you can solve for the Reynolds number of the flow. Reynolds number basically is rho UH divided by viscosity. You can simplify that down to being just rho Q divided by viscosity. And you can just use that equation and apply it to all of these guys. But for Couette analytical, that basically simplifies down to rho UH divided by 2 mu. And that's 40. And Couette, you can just plug in the finite differencing that you got earlier. You can also get 40. Pascal analytical ends up being rho 12 mu squared multiplied by negative dp dx multiplied by h cubed. And that gives you this number. And Pascal finite differencing, same thing as Couette, just plug in what you got for the Q FD of Pascal finite differencing. And that ends up getting a slightly different number than Couette analytical, but that's running errors that is to be expected with that calculating method. And this is my Excel document that I did. I don't know why I made a entire column for dy. It's really up there. Oh well. Cool. Please let me look out for this. Thank you.